I've always heard stuff like the physics used in our day to day life is quite different from the physics observed at the quantum level. Subatomic particles follow a mere probability function. Phenomena such as quantum entanglement have been seen where a single particle can exist in not quite in two different places. It's not That's not how it works, but I'll come to that. What do you think is the reason for such an enormous difference in the physical state of bodies that coexist in the same universe but have to follow different laws of physics? Well, they don't follow different laws of physics. They follow the same laws of physics. But we see the macroscopic world, the ordinary world that we inhabit, differently. And the quantum effects aren't that apparent at all in the ordinary mundane world that we live in. But when you zoom in, like hyper zoom in, then you will see atoms and molecules and subatomic particles like protons, neutrons, electrons, and quarks and whatnot. And these particles, they obey the rules of quantum mechanics. So at some stage, at some scale, the ordinary world that we are familiar with, this ordinary world emerges from the quantum scale, from the quantum world. Okay, it does emerge from the quantum world. So how does that happen? Yeah, that's the question. So what kind of laws do quantum objects follow or obey? You have like you said, entanglement, but entanglement doesn't mean that a particle is in two places at once. It means a pair of particles that are described by the same wave function can be as far apart as you want, maybe a light year, maybe 100 light years, but some of their properties are correlated. So if you look at one particle, you'll immediately know what is the corresponding properties, what are the corresponding properties on the in the other part of the other particle, no matter how far away it is. But it doesn't mean there is faster than light communication or any such thing. So that's a little difficult to explain, but that's not how it works. I'm sure you watched some science fiction series like the three body problem or whatever, in which they're communicating through entanglement. That's not how it works. That is so wrong. That is so wrong. So entanglement means two particles. You can have more, but let's say you have two particles that they are described by the same wave function, and some of their properties are correlated. Let's say, very very silly and very straightforward comparison or illustration. Let's say you have a pair of gloves. Okay, I have a pair of gloves, one left-handed glove, one right-handed glove. I put one in one box, another in one box. I send one of the gloves to London. I send the other glove to Moscow. Okay, and I myself don't know which glove is in which box, which one has gone to Moscow, which one has gone to London. Now my friends in Moscow and London, the moment they open the box, they will know exactly which box is there in the other place. That's kind of how entanglement works. So at the subatomic level, you have entanglement, you have superposition, in which particles exist in multiple states. In a superposition of multiple states, there is the observer effect, the collapse of the wave function. The moment there's a measurement or an observation, the wave function collapses. That is something you don't see at the classical level, at the macroscopic level. Uh, there are all kinds of other phenomena that are very. There is quantization, obviously. There is wave particle duality. So particles can behave like waves as well as particles. The electron can behave like a wave. It can also behave like a particle. Photons, which are massless, can behave like particles as well as waves, and so on. And you can prove this using experiments like the double slit experiment and all that. But such phenomena are not visible at the classical level, at the macroscopic level. But these macroscopic phenomena emerge from the quantum level. So what happens? See, for example, and it's because of the wave. It's because of the wavelength. See, the wavelength, de Broglie wavelength of a particle is the smaller the particle is, the larger the wavelength is, and the larger the particle is, the smaller the wavelength is. So quantum phenomena are become apparent, and they take precedence over classical phenomena when the wavelength is significantly large. So photons have different wavelengths depending on the color of the light. This is blue. You're seeing blue photons emerging from this fabric here. You're seeing orange photons from behind. So the light, it tells you the wavelength, kind of, if you know what the wavelength of what color is, and so on. But this ball, it also has a de Broglie wavelength, but it's extremely small, and that's why the quantum effects are not apparent. And when you, you can even solve the Schrodinger equation for the Earth Moon system or the Sun Earth system. And what it will give you is gigantic quantum numbers, principal quantum numbers, and all that, and energy levels. So the larger the quantum numbers and the larger the energy levels, the less apparent the quantum effects are. So that's what it is. And then there is the correspondence principle. Niels Bohr came up with the correspondence principle, which essentially says that the larger the quantum numbers and the larger the energy levels, etc., the less apparent the quantum effects are. So because of that, what we have is that the ordinary mundane macroscopic world, it actually is a quantum world, but we don't see the quantum effects because they are not visible enough. But there are certain objects, certain phenomena that are purely quantum at the macroscopic scale. Bose-Einstein condensates. Most of us obviously will never see them, but those are macroscopic quantum objects, phenomena, macroscopic quantum phenomena. That's one. Neutron stars. Well, we don't really get to see them, but those are quantum objects, gigantic nuclei, essentially, atomic nuclei. Then you have crystals. You see this? This is an ordinary quartz crystal. It's a crystalline object. The properties of this crystal are purely quantum mechanical. Okay, the hardness, the shape, the angle of at which light reflects, the colors, all of this is purely quantum mechanical. This is a purely quantum object. This is a macroscopic molecule, essentially. So there are certain quantum effects that we see, are visible. We may not realize it, but overall, everything that exists at the classical level, the macroscopic level, emerges from quantum mechanics, from the quantum world, via the correspondence principle.